He works at the intersection between machine learning and planning, with a focus on robotics application. So he uses a wide range of techniques from I think using about learning, program synthesis, and also text and motion planning. And I think his work has been always very exciting to me because he introduced a coherent framework to combine both learning and planning to solve very hard problems in robotics. So I'm very excited to have him here today to talk about his work. So that's how welcome Tom.
Thank you so much. And thank you all for being here, especially during spring break. Appreciate it. Hopefully this is fun. So I'm excited to tell you about some of my work on learning and planning with relational abstractions. I'm sorry, there's a bit of a delay, I think, between the Zoom and everything else. So this is a spot robot that might look familiar, which we're working with right now at the Boston Dynamics AI Institute. And we're developing learning and planning techniques so that we can give Spot goals like, hey, Spot, put away the tools. And then once we tell Spot what we want, the hope is for it to quickly start to take actions towards achieving that goal. So here it's going to pick up that measuring tape. It'll work on putting away that brush. It realizes it has to retry a couple times because grasping will fail. Pick up that drill. And last but not least, it tries to get the hammer, but it realizes that it needs to plan a different way to get the hammer because it's too high to reach directly. So the hope with this learning and planning is that we can one day have robots that serve very general purposes in society. So we want to have robot, chefs, robot lab assistants, robot house cleaners, beekeepers, anything that you might want to have a robot help you with in your daily life. We want to have a robot that can do that.
Okay. We turned here on Zoom.
Oh, okay. Let's see. What can we do about that?
Can you
It's already unmuted. Maybe I'm just standing too far away.
I can hear you fine.
Yeah.
Oh, other
okay.
people. So maybe it's okay. Okay. I'll just make sure to stay close to here. Thank you. So to achieve this very general purpose robot, what we're going to need to have is some kind of robot factory like Boston Dynamics say that creates the robot hardware, and then the robots will be shipped off to many different kinds of deployments. So we might have, let's see, these Spot robots that are coming from the robot factory. Here they come, and they'll be shipped off to, for example, coffee shops, homes, hospitals, restaurants, among many other kinds of deployments. Inside the robot factory, we're going to want to create robots that are good in general. So the engineers in this factory will be thinking about sort of the most common cases that come up across a wide range of deployments. And they'll be engaged in very general purpose kinds of programming, thinking about these common cases. We need to turn on the left corner. Oh, maybe, I don't know if that's an instruction.
Turn on the left corner.
Is this for you?
I don't know.
I think it's for you. I don't think so.
Okay, all right, sorry, I'm just gonna keep talking. So part of these general purpose programming efforts these days might be pre-training large foundation models, right? And so if we look at a lot of the efforts that are going on in industry labs today, a lot of them are of this flavor where we're training very large models using, oh, thank you, very common, big data sets that cover these common cases. And really this is getting us ready for what will be, I think, the robot factories of tomorrow. But after that, the question will become, what should these robots do once they're deployed? And I think what we want is for the robots to become experts in their domain once they're deployed. When I say domain here, I don't mean the domain of household robotics broadly. I mean, we want robots to become experts in your home with your goals and your preferences and your objects and your constraints and everything that's unique to you. So we're going to want robots that are capable of learning to specialize during deployment. And we're also going to need robots that are capable of planning and reasoning in the moment once they're deployed, because we're going to be solving very difficult tasks like clean up an entire room with all this clutter and considerable variation, not only within a single house, but between houses. So these are very difficult tasks that really require intelligent planning and reasoning. So these deployed robots are going to need to be efficient and effective in a couple different ways. So first of all, we're going to want our robots to be time efficient. And so when I say time efficient, I mean we don't want to have sort of philosopher robots that spend hours or days thinking about what they're going to do before they take any actions. We want them to start acting almost immediately. We also want robots that are data efficient. So we're going to have these robots learning during deployment. That means they need to learn a lot from just a little bit of experience. And we also want them to be human efficient. And what I mean by that is they should ask for help and ask questions of people when people are available, but they shouldn't be constantly bothering people. We want them to be autonomous. And we also certainly don't want to assume that there's sort of an expert programmer deployed with the robot. We want these to be very scalable general methods that are truly autonomous. And most of all, we want these techniques to be effective. So we want our robots to actually solve the hard tasks that we're giving them. So when we think about some of the paradigms that are available today for this kind of online planning and reasoning, one common paradigm is AI planning and task and motion planning, which in my background is an example of that. And this kind of AI planning is great because over several decades of work, we now have very powerful solvers that if you give them the right kind of representation of your problem, then they'll work really hard to figure out what actions should the robot finally take. One of the drawbacks of AI planning, though, is that it tends to be quite slow, especially in large problems with lots of objects and clutter and high dimensionality. But the biggest issue is that to even use these solvers in the first place, you need to have a bunch of different domain-specific models that are typically programmed in a lab by a human engineer. So this is a huge bottleneck for using these kinds of techniques in the wild during deployment. And traditionally, these are approaches that don't involve learning. So there's really no improvement as the robot continues to see the same kinds of problems over and over again. Another paradigm which has made a lot of progress for the last 10 to 15 years is reinforcement learning. And reinforcement learning is great because what you get at the end of the day is a policy, which might be a big neural network or something, that if you give it an observation, then it'll quickly give you an action to take. So it's very time efficient. And these approaches are also quite human efficient in the sense that they're generally applicable. So there's a certain amount of design going into reward functions and observations and action spaces and so on, but these are quite general techniques. In practice, reinforcement learning tends to work best when we have relatively narrow distributions of tasks and relatively short time horizons or very dense feedback. But most of all, reinforcement learning is notoriously data hungry. So really, this works best when we have, for example, a simulator that we can use to generate arbitrarily large amounts of data and then learn from that. So reinforcement learning, I think, is a very powerful tool to use maybe in the robot factory, but I think we're going to need something more once the robots are deployed.
And making it in my own house.
In your own house, absolutely. Yeah, we don't want to have a robot that's randomly exploring in your house and breaking everything, for example.
Versus some Amazon factory.
Right.
Yeah.
Exactly.
Yeah.
So most recently, over the last couple of years, there's been a lot of excitement around how can we take advantage of these large language models or other kinds of foundation models for doing this online decision making. And this is something that's been very interesting to me as well. And similar to reinforcement learning, there's the prospect of being very time efficient because you can just do another big pass through a neural network. But what's really cool about these models is that they can generalize quite a bit. For example, through few shot prompting, where you show them a couple examples and ask them to solve a new problem of the same form. There's a certain amount of prompt engineering and validation that goes into actually using these approaches in practice, so there's not entirely human efficient. But the biggest issue is that what we've seen in practice is these approaches on their own are really not well equipped for solving the truly long horizon, truly difficult reasoning and planning problems that come up in these kinds of robot domains. And I'm hoping to give you kind of a sense of why that is as I show you some of the example problems that we're talking about. But nonetheless, I think these kinds of models are very powerful and we can use them in many different ways. And we've already started to look at this, and I'll mention a couple of other ways at the end of the talk. But what I really want to focus on today is a different kind of paradigm, which I'll refer to as learning to plan and planning to learn with abstractions. So this is going to be an approach where we're going to learn to plan quickly from past planning experience. So we're going to get more and more time efficient as the robot continues to see the same kinds of problems. We're also going to be very data efficient by imposing a lot of structure into the learning that we're doing and generalizing a lot from just a little bit. We'll be human efficient because we're not going to require an expert programmer to come in and specify all these domain-specific models. We're instead going to have the robot learn these domain-specific models online automatically. And finally, we're going to be effective in solving large, hard tasks by leveraging these powerful solvers that we have from AI planning. And we're going to do that by learning these domain-specific models in a way that allows us to take advantage of these solvers. So let's jump in and let me start by describing what exactly do I mean by planning for the purpose of this talk. So at the end of the day, we're going to have a robot like Spot Robot, and we're going to give it a goal like, hey, Spot, what are the tools? And so we'll have some initial state and we'll have some goal. And we somehow want to have a planner that's capable of sequencing together these actions that will eventually achieve the goal. And the question is, what's actually going to be going on inside this planner? Well, first of all, we can note that the robot has certain sensors. So this robot happens to have cameras in its hand and on its body, and we can take images, and we can use tools from computer vision to, for example, recognize objects and features of objects. So we can leverage all these advances in perception to construct a much more structured view of the world. So we're going to now say that we are detecting these objects and these continuous features of objects, and we'll now have this nice structured object-centric view of the state where there's a hammer and a bucket and the robot itself is treated as an object, and we're detecting these continuous features of each of these objects. So that gives us a much more tractable problem to deal with. We're imposing all this structure at the level of the state, but we still have a very difficult decision-making problem here. That's because We're going to be reasoning over very long time horizons, hundreds or thousands of actions. They're going to be continuous states and actions, generally speaking. We're not giving any kind of like dense feedback as we're doing this reasoning. We just have a sparse goal, and there's typically difficult constraints to reason about as we're doing this planning. So this remains a very difficult decision-making problem. So to make it more tractable, we're going to introduce a kind of state abstraction with the hope that we can sort of focus on what's most important in these object-centric states to start to reason and plan at this higher level. And I'm going to be talking about a particular kind of state abstraction that uses what are called predicates. Predicates are relational classifiers over object states. So to explain what I mean, let's take a look at a kind of standard benchmark domain, which is this block stacking domain, where there are these 5 blocks here, and there's a robot, which is also itself an object. And the object-centric state for the image shown here is in that table where we're tracking the XYZ position and the size of the objects. So we might have a number of predicates, perhaps these 2 predicates shown here. The top one is called onTable. And the definition of this predicate is it takes in a current state and it takes in a block, which we want to know whether that block is on the table in this state. And this is a super simple definition of the meaning of onTable, which just looks at the z position of the block and says whether or not it's less than some threshold. And that's the definition of onTable for this environment. We might have another predicate called on, which just looks at the relationship between 2 blocks and their positions and sizes and uses that to determine a very simple definition of what it might mean for one block to be on another in a state. So if we have these predicates, then what we can do is we can run these classifiers over all combinations of objects in a given state, and we can record all of the ones that evaluate to true in that state. So that's the abstract state that's shown in the top bubble there, where these are the sort of ground predicates that hold true in that state. So we're throwing away all the continuous information in the continuous in the low-level state. And in this example, we've lost information about the robot, but the hope is that these abstractions will still be a useful summary that the robot can start to use for reasoning and planning at this high level. So this is a kind of state abstraction, but this is still actually kind of a complicated abstract state. It's combinatorially complicated. And so to do this reasoning at this abstract state, we're going to introduce another kind of abstraction, which will be a kind of action abstraction. And this will be what I'll refer to as skills. So skills are going to be responsible for sort of reasoning in this abstract state space about what abstract states can be reached from other abstract states. So concretely, a skill is going to have an operator. So for anyone who might be familiar with strips or PDDL, these are from the AI planning literature. That's the kind of operator that I'm talking about here. But for anyone who hasn't seen these before, here's an example operator for a skill called pick from table. So the skill has arguments, which are like placeholders for objects. So if we're talking about picking from the table, there's some block that we're going to pick and a robot that we're going to use to pick it. There are preconditions, which characterize what are true in the abstract state in order for us to consider using this operator. So in the example of picking from the table, the robot's gripper should be open if we're going to pick something from the table, and the block that we're picking should also be on the table. And then finally, we have effects. And these are what says what would actually change in the abstract state if we were to do this skill. So we have add effects, which are what gets added to the abstract state, and then delete effects, which is what gets removed. So in this example, what gets added when you're picking something from the table is that you'll be holding that block. And what's deleted is that the robot's gripper will no longer be open and the block will no longer be on the table. So altogether, this is an operator, and it's a sort of lifted representation because we're not talking about specific objects yet. But we can take an operator and we can ground it by substituting in specific objects for those placeholder arguments. And then we can end up with a ground operator like the one shown there, which is talking about specifically picking up block 1 with a particular robot gripper. Once we have these ground operators, then what we get is effectively this abstract transition model where we can run our predicate classifiers in a current state, see what abstract state are we in, and then we can consider all the ground operators whose preconditions hold in that abstract state and anticipate what the next abstract state would be under the effects of those operators, and we can start to do some sort of search and planning and reasoning in this abstract state and action space. So why are we committing to these particular kinds of state and action abstractions when there's a big family of other kinds of abstractions that one might consider? Well, the reason is that we want to be able to leverage these very powerful AI planners that have been developed over several decades. And if we have these predicates and operators, then we can literally just download, off the shelf one of these very powerful planners, give it the right kinds of predicates and operators, and it'll really quickly return to us a long horizon plan. So for example, here are some kind of standard domains that are well suited for these kinds of planners. So we have a blocks problem, a Sokoban problem, a tower of Hanoi problem. And you can see, for example, this is a tower of Hanoi problem with a length of 579, and just running this on my laptop, and it's found a plan of that length in a fraction of a second. So these are very powerful solvers that we can take advantage of. For solving robot planning problems, though, we aren't done yet because we need to figure out what actions should the robot actually take in the real world. And so to solve that problem, what we'll do is we're going to view these abstractions that are coming out of the symbolic planner as a kind of constraint that we can then use to set up a continuous optimization problem to ultimately find actions for the robot to take. So we have this symbolic plan coming out of the symbolic planner, and conditioned on that symbolic plan, we're setting up this optimization problem which says, find me low-level states and actions, continuous states and actions, that are consistent with sort of the sketch that's coming out of this symbolic planner, and ultimately are also consistent with the environment dynamics. So this symbolic plan is sort of serving as useful guidance for solving this continuous optimization problem at this low level. So that's how I like to think about these abstractions, as providing guidance for reasoning and planning at the low level. Yeah, Jason.
Is K in the 0.1 here meant to be fixed?
It's not, yeah, I wrote that for
Okay.
simplicity, but it can vary.
Okay.
Yeah, thanks for clarifying. Yeah. Very good. So altogether, this is a sort of bilevel planning because we're doing this symbolic planning at the high level, and we're also doing this inner sort of continuous planning at the lower levels. And this is one kind of a broader family of techniques called task and motion planning. And we have this survey paper on task and motion planning if you'd like to read more about it. Historically, task and motion planning has sort of emerged from seminal work in the 70s on Shaky the robots and A-star search and other like very foundational methods at SRI and other places back then. And one of the ways that we've made progress since then is in terms of the length of time that the robot can operate autonomously, so the horizon of the problems that are solvable. But we've also made problem in terms of generalizability. So we're now able to solve much more general classes of problems than we were able to back then. But the way that I understand a lot of my work is how can we continue to make progress along both of these axes, and in particular, how can we improve on the generalizability or scalability of these techniques? And really the key bottleneck is in using task and motion planning, you're typically required to hand design these predicates and operators and all these models that are necessary to use these task and motion planning techniques. So that motivates my work on learning instead to make task and motion planning possible by learning these models automatically.
Although I guess another thing on the history is that in those days, the computer vision wouldn't work nearly well enough for
Absolutely.
you to use it.
That's right.
And I guess now it's possible to get things, take objects on top of other objects. So
Yeah.
that means the input is sort of there, I guess.
Yeah, absolutely. Yeah, I think we're able to do things now just by using these computer vision techniques that we wouldn't be able
Yeah,
to
no,
do.
it's sort of like going back 40 years. People
Right.
would have loved to do this. Computer vision wasn't come forth, let alone with theory, but
Yeah, absolutely. Yeah.
okay.
Awesome. So yeah, this is setting up my work on learning to plan. And specifically what we want to be able to do is learn the predicates and operators that when we use them as constraints inside of this bilevel planning, it leads to efficient and effective planning. So to start talking about how we can learn these predicates and operators, let's first talk about a simpler problem where suppose that we are given predicates to start, and we're also given demonstrations of entire tasks of interest like the one shown in this video here. So if we have these predicates and we have these demonstrations, one question is how can we learn operators for planning on other kinds of problems in the distribution of tasks that are being demonstrated to us? So I'm going to walk you through very quickly one kind of way that we can learn operators if we're given predicates. So what we can do is we can start by taking these full task demonstrations and segmenting them into sort of like keyframes where ultimately we want to have a skill that's changed in between these keyframes. And there's different ways that we can do this kind of temporal segmentation. One signal that's very useful is looking at contacts between objects. So often we'll segment a frame when there's a new contact with an object, for example, but there's other ways that one might go about this. Once we have these segmented trajectories, then we can take the predicates that we're assuming for now are given, and we can apply them to all these keyframes and look at the abstract states in each of them. And then we can look at the differences between these abstract states. And these differences are what's getting added and what's getting removed in between each of these subsequent abstract states. So you can imagine these are ultimately going to look a lot like the effects of the operators that are characterizing these skills. And these differences are going to be a signal that we can use to actually partition all these transitions into their own transition sets. And these sets are going to correspond finally to skills, one skill per set. And we'll do this in a way that's looking at, the differences, but while being equivalent up to object substitution. So for example, if in one transition we resulted in holding a hammer and another transition we resulted in holding a water bottle, we would put those two transitions into the same transition set because they're equivalent except for the objects that are sort of bound in that transition. So once we have these transition sets, we basically for free get these effects that are used to describe the skill operators. And then to compute preconditions is almost as easy. all that we basically do is look at what's in common among all of the initial states in each of these transition sets. So we do a big intersection to find all the things that are in common. And that's pretty much all we need to do to very quickly learn operators for the demonstrations that were given to us. So we end up with one operator per transition set like shown here. So that's what we can do if we're given predicates. But the much harder question is, how can we come up with predicates in the first place? So to make that tractable, let's start by talking about an easy version of this, where suppose that we have data that's of this form, where we have states and we have ground predicates and we have labels saying in these states for these ground predicates, yes, they hold or no, they don't hold. So suppose that we just been handed this kind of data. If we had such data, then we could very easily take advantage of whatever supervised learning technique you want to use to train classifiers to understand the meaning of these predicates in these states. So we can use neural networks, or we could use whatever your favorite kind of binary classifiers might be. And often we do that. There's a little bit of care that we need to take to deal with the fact that these are relational classifiers rather than just standard classifiers, but there's a number of ways that we can handle that as well. The downside of this approach, though, is that we need to assume that whatever predicates are sort of available to us in this data are going to be the ones that we ultimately want to use inside of bilevel planning. And we need to assume that those are known in this data. And in practice, these predicates that might, for example, correspond to natural language concepts may not be the ones that are most useful for efficient and effective planning. So naturally occurring data might not be what we want. And we're also, making the obvious restriction that somebody's handed us this data in the first place. So that doesn't seem like something we necessarily want to assume if we're doing this during deployment. So instead, we'd like to solve a much more flexible but more difficult version of this problem, where we start just with the same demonstrations that we were going to use for operator learning, but without any kind of label or knowledge of the kind of predicate or the number of predicate or the structure of the predicates at all. And we're just going to leave it up to the robot to invent any predicates that it wants. So if we can do this, we're going to be happy because it requires far fewer assumptions. We're not assuming anything about labeled predicates being given to us for the structure. And there's the hope that since we're leaving it up to the robot what predicates it wants to invent, maybe the robot can choose predicates that are explicitly optimized for fast planning. The downside of this approach, though, is that, of course, it's a much harder problem because we're lacking this supervision. But nonetheless, it's a problem that we have some techniques to solve, and I want to tell you about one of those techniques now. So to make this tractable, we're going to set this predicate learning problem up as a kind of program synthesis, where we can look at these predicate classifiers that I showed here and say, well, those are simple programs. I wonder if we could learn programs that look something like this automatically rather than writing them down. So that's what we're going to do. And we'll start by defining a grammar which characterizes a space of predicate programs that we're going to search within. And we'll do a very simple thing, which just starts by enumerating a big pool of candidates from that grammar. And then we're going to be searching within this pool for predicates that we'll finally hold on to as our final set of predicates. So we'll start with this pool of candidates. And to select the predicates that we're going to keep, we'll perform a hill climbing search where we start with the empty set, saying we're not going to keep any predicates. And we gradually add one predicate at a time at each level of this hill climbing search. So we'll go through and we'll add one at a time, and deciding at each step which is a set of predicates that's most valuable to keep at this level. And then we'll keep going until we can find no improvement. Yeah.
Sorry, are these predicates executable at this point?
Yeah, they're programs that we can execute on the state. Yeah.
And that's because they're written in terms of primitives that have been hard-coded?
That's right. Yeah.
I see. Okay, so they're not looking at pixels, for example.
Exactly right. No, they're all operating on the object-centric states. So yeah. So the key question that's really going to be driving this entire hill climbing search is, what is the objective that we're going to use to decide what predicates are worth keeping? And this is really
about hill climbing. Do you get local minimum? Or?
We might get local minimum. That's something we were concerned about. So we implemented like enforced hill climbing and variations that would allow us to escape from local minimum. But it turns out that in practice, hill climbing actually worked quite well. Yeah. So,
okay.
Yeah. But that, in theory, it could be a problem. So yeah, what is this objective that we're going to use to decide what predicates are good? Well, we can look at the literature on state abstraction learning. We're talking about learning a kind of state abstraction in the form of these predicates, and we can say, maybe we can take advantage of existing objectives. So one such objective is reconstruction, which basically says a set of predicates or state abstractions are good if they're as good as possible for reconstructing the states before the abstraction. And there's other ideas like in the MDP literature on homomorphisms and bisimulation, but we found that in practice, all these objectives are not sufficiently tied to what our real objective is, which is that we want to finally learn predicates that lead to efficient and effective bilevel planning. So our real objective would do something like the following. So let's say that we have a candidate predicate set like the one shown here, and we have demonstrations that are available. What we would do ideally is we would take those demonstrations and we would take the candidate predicate set and we would run our operator learning technique to end up with operators that use those predicates. And then we would take a task that was demonstrated to us as being important, and we would actually run our entire bilevel planning system and record the amount of wall clock time, for example, taken by the entire bilevel planning system here. And then we would note down for this task, what was it finally solved, and how much time overall did planning take. And we could do this again for a second task that was demonstrated to us as being important. So running our entire bilevel planning system, recording the time, and recording whether it was solved. And ultimately, we would combine these somehow and say, we want to solve as many tasks as possible while doing so as quickly as possible. So this is what we really care about. The problem, though, is if we were to actually use this real objective inside of a hill climbing search, for example, it would be completely intractable. It would just be way too slow to do this in practice. So what we're going to do instead is we're going to introduce a surrogate objective, which is faithful to this real objective, but is going to be actually tractable to evaluate. And we'll start by noting that really the thing that's most intractable about this entire procedure is this inner continuous optimization part, especially when we're talking about predicates that are really not sufficiently rich early on to serve as useful constraints for this continuous optimization. So this turns out to be the most intractable. On the other hand, we can explicitly run a symbolic planner and record the amount of time taken because these are very fast planning techniques that we can measure. So what we're going to do is we're going to use the demonstrations that we have to come up with an approximation of this inner intractability. And so what we really need to do is somehow use the demonstrations to estimate a probability that if we did run the full continuous optimization, what is the probability that doing so would succeed? And it turns out we can do this in a very simple way that just looks at the sort of costs of the abstract plan versus the cost of the demonstration. When I say cost here, I just mean the number of steps in each of those abstract plans or demonstrations. And we'll say in this geometric distribution, what this is saying is there's a higher probability of us being able to successfully do continuous optimization if the cost of the abstract plan is similar to the cost of the demonstration. So this is just looking at the cost. It's very simple. And what the intuition is here is if we have an abstract plan coming out of the symbolic planner that's cheaper than the demonstration, then that should be kind of suspicious. It's like, why wouldn't the demonstrator have shown us what seems to be a better, cheaper abstract plan if such a thing were possible? And on the other hand, if we have an abstract plan that's more expensive than the demonstration, that's just plain bad. So we want to sort of match the demonstrator, assuming that the demonstrator is near optimal as best we can with the abstractions that we have. So this is just the sort of kind of simple answer to the question of how we can avoid doing the full continuous optimization. And that's the final ingredient that we need to drive this entire predicate learning procedure. So let me now show you a couple of results, sort of getting a sense of qualitatively what this looks like. So this is very small font, but just to give you a sense of like the number of predicates and the operators that we learned with those predicates. So the top left box there is, I think, 18 predicates that are learned with this procedure, and the rest are operators that are learned with those predicates. And this is a tool use domain. And what's nice about these being all programs is that we can inspect these learned predicates and understand what they mean. And we can see that in this case, they correspond to intuitive concepts like a nail being held by the robot or a screwdriver being small enough that the robot can grasp it. We also see that planning with predicates that we learn is very time efficient, especially when we're talking about planning on problems that are much larger, longer horizon, more objects than what was seen in the demonstrations. So these are plans found with learned predicates in block stacking and a sort of painting domain. And these are much more objects than were shown in the demonstration. And empirically, we see that planning with our learned predicates is much faster than planning with predicates that are learned by different baselines, including what was the best baseline from the abstraction learning literature by simulation. And what's cool is we also see cases where planning with predicates that we learn is actually faster than planning with predicates that are written down by hand. And I'll show you an example of that in a little bit. Another thing that we see is that this entire procedure is very data efficient, owing to the fact that it's a very structured kind of learning. So we can look at the number of demonstrations or number of training tasks and see how do we do in terms of evaluation performance on held out tasks as we have a certain number of demonstrations. And it turns out that on the order of like 25 to 100 demonstrations are often enough to learn predicates that lead to very efficient and effective planning. And we also compare to a number of baselines. We often use graph neural networks when we're comparing to different kinds of pure deep learning approaches. And that's because we're dealing with these object-centric relational states and actions. So we need to have some kind of network that can use relational kinds of inputs. So we like graph neural networks here. Another cool thing is that the predicates that we learn with this procedure are task aware. So what I mean by that is, suppose that we just have a task distribution where what the robot needs to do inside of the task is it needs to pick up these cylinders and put them into the shelf. So this, if we just have tasks that sort of look like this, then one of the predicates that we all end up learning basically refers to whether the object is held or not, so a predicate called holding. But if we change the task distribution so that sometimes these objects need to be put into a shelf, and other times the object needs to be put into a box, then there's now this important distinction about whether you've grasped the object from the side versus whether you've grasped the object from the top, because we need to be careful about having the robot's wrist collide with the ceiling of the shelf or collide with the sides of the box. And our predicate learning system automatically discovers that this is the important distinction that should be modeled at this abstract level, and it now learns two different predicates for holding that distinguish between whether the object is held from the side or held from the top. And a final cool thing about this is that the predicates that we're learning are sort of aware of the planner that we're using inside of our bilevel planning scheme. So for example, if we run our entire predicate learning system on this block stacking domain with a certain configuration of the symbolic AI planner, then we see that what we learned with this AI planner is basically the standard set of predicates that are most often used in this block stacking domain for a long time. But if we change the AI planner, we found that we learned a sort of strange looking set of predicates, which is almost the same, except instead of nothing above, it learns these two different predicates, which seem to be almost logically equivalent, but are not quite the same. And so at first we thought maybe this is a local optimum of a hill climbing search, or maybe this is syntactically equivalent or something. But then we saw that planning with this second set of predicates was actually 30 times faster than planning with this first set of predicates, owing to some weirdness inside of the AI planner that our system has discovered automatically and is taking advantage of to perform very fast planning. So this is quite cool to see. And this is really speak to the fact that this is a sort of explicitly optimized for fast planning, which is nice. So altogether, what this gives us is a way to learn these predicates and skill operators for doing this kind of bilevel planning. But at this point, I want to sort of unpack a little bit what is actually happening inside of this continuous optimization box that so far I've been very handily about what's happening here. So let's talk about how would we actually go about finding continuous actions to implement the abstract plans that are coming out of these symbolic planners. So one thing that we might do is extend the definition of a skill as I've described it so far. So far we've thought about these skills as sort of abstract actions that reason in this abstract state space about what abstract states can be reached from other abstract states. So we have these operators for describing how the robot might, or what abstract states we're trying to get between. But perhaps we should introduce another component to a skill, which is like a policy, which tells the robot how to actually execute an abstract state transition. So typically these will be symbolic operators that we've seen how we can learn. And when we're going to learn these policies at the end of the day, we'll often do so with neural network techniques. But the important thing is that these policies are now going to be interfacing with continuous states and actions. So for example, we can take a look at this planning architecture that we've been building out. And now the symbolic planner is going to be outputting these skills. But then the skills will have these policies which look at the current low-level state and output low-level actions and operate in closed loop with the environment. So outputting actions, receiving states, outputting actions, receiving states, and then finally terminating once the skill has reached the next abstract state that's predicted by the operator of that skill. So this seems reasonable, but and here are some examples of what this might look like in a block stacking domain, where maybe we have a policy for pick from table, and so we see that many actions are being taken until we finally achieve the abstract state transition where the robot results in picking the block. And these are two different sort of groundings of the pick from table skill, and the policy, like the operator, is going to be relational. So we can use the same policy with different groundings like pick block 1 or pick block 2. So if this is what we're going to do at the end of the day, then why did I go through the trouble of describing this as a continuous optimization problem, where it seems like we're just kind of hiding that inside of this reactive policy? Well, the reason is when we go beyond block stacking and we look at more complicated kinds of domains, we might find that the abstractions, as I described them so far, are kind of liars in the way that's suggested by this dog trying to get the stick through the door while ignoring the geometry of the stick, if you will. So to better explain what I mean by these abstractions might be liars, let's take a look at this other domain from Dan Fei and colleagues, where what they were looking at is this tabletop environment where there's two things that you might want to do. So one thing you might want to do is get that red block onto this green platform. And to do that, you need to actually use this hook as a tool, because there's this reachability limitation that's illustrated by that transparent wall, which says that the gripper can't reach beyond there. And so instead, the robot should pick up this hook, pull the red block from beyond that transparent wall, pick it up, and then put it onto the green platform. The other thing that you might want to do in this domain is get the blue block onto the green platform. And for that, you need to use this hook again to get that blue block out of the tube. But this time, you're going to grasp the hook at the top, and then you're going to poke the blue block through the tube, and then pick it up and then put it onto the platform. So in both cases, we're using this hook as a tool. But in the first case, we're going to grasp the hook at the bottom, and in the second case, we're grasping it at the top. So let's think about what if we were to sort of apply the skill abstractions as I've defined them so far to this domain. So perhaps we would have an operator that looks something like this for characterizing the skill of pushing the blue block out of the tube. And what this says is if you're in a state where you're holding the hook and the blue block is in the tube, then you should be able to get the blue block out of the tube. So if you find yourself in a state where you just grasp the hook from the top, then everything is good, right? We can in fact get that blue block out of the tube. But if instead we find ourselves in a state where we just grasp the hook from the bottom, then it's not really the case that we can actually get that blue block out of the tube because of the specific continuous state that we found ourselves in after grasping that hook. It's because we grasped it at the bottom instead of the top. So it's in this sense that I'm saying that this particular abstraction is kind of a liar. We have these preconditions saying sort of if you're holding the hook, then you should be able to get the blue block out of the tube. But depending on how exactly you're holding the hook or what specific low-level state you're in, that may or may not be possible. So what should we conclude from this example? Well, one reasonable conclusion would be the issue is in the predicates that we're using in the preconditions of that operator that I just described. So maybe we want to have a distinction between holding top and holding bottom, and maybe we want to be able to learn that distinction and learn new predicates as we saw that we can do before. And I think that in this simple case, that's actually kind of the right answer, right? This is a case where it would make a lot of sense to have two predicates, one for holding top and one for holding bottom. But as we consider more complicated geometric domains and kinematic domains with lots of complicated constraints, we don't want to force ourselves to perfectly model all of this complexity at the abstract level. That's going to just be forcing the problem into the abstract space, and that's going to quickly blow up as we move into more complicated robotic domains. Another thing that we might try to do is say that, well, really the problem was in the policy. So maybe in this example, the policy should be improved so that actually the policy itself can regrasp the tool internally, and then it can achieve the abstract transition of the operator as I described it. And that is something we'd like to do, learn better policies that are sort of better at sort of implementing the operators. But again, we don't want to just force all the complexity into policy learning. So instead, I think what I'd like to focus on here is a third interpretation, which says that really it's the planner that's to blame in this example. And the problem is that the planner is trusting the abstractions that it has too much in the way that I've described it. So what we should do is we should go back to viewing these abstractions as a kind of guidance for low-level planning instead of a replacement for thinking at all about the low level once you've done the abstraction. So let's zoom in a little bit more on this third interpretation. So the abstractions might be liars, but that's okay. All models are wrong, but some are useful. And I think that these particular kinds of action abstractions can still be useful. But to make them useful, we're going to extend them a little bit further. And we're going to introduce a continuous parameter space to the skill that allows us to reason about many, many different ways, an infinite number of ways of achieving each skill. So in the case of picking a skill, for example, we might have a continuous parameter space that refers to different grasps of a tool, for example. So this is now like a degree of freedom that the robot can reason about when it's planning, giving it different ways that it might accomplish the effects of holding a tool. And once we have these continuous parameter spaces, then during planning, we can optimize in these parameter spaces and try to find parameter settings that will allow us to satisfy the entire sketch coming out of the symbolic planner. So if at first we have a parameter corresponding to holding the hook at the bottom, then we'll see that later on we're not able to satisfy the entire planned sketch. And so we'll need to backtrack and realize that maybe a different parameter is necessary, like one that holds the hook from the top, and then we'll be able to finish the rest of the plan in this example. And you'll see that there's another component that came up here called a sampler. And the sampler is another learned thing that we're going to include as part of the skill. It's another neural networking practice that proposes different parameters for us to consider when we're doing this kind of optimization. So altogether, we're going to be we want to be able to learn these parameterized skills that will give the robot this flexible way to move between different abstract states when it's doing this kind of planning. And so what we need to do is learn operators, as we saw, learn policies that are parameterized, and then also learn samplers for those policies. So we have a number of different works looking at learning each of these different components and doing so in a mutually compatible way. We've done this in a lot of different kinds of environments, like the one shown here. And we have this stack of tools that we can use all together to learn these kinds of skills. And when we're doing this, a key consideration is often how can we learn these skills from just a little bit of data, often demonstration data, that allows us to generalize quite a lot. And the answer to that data efficiency question often is imposing a lot of structure into this skill learning. And I often like to think about a kind of neurosymbolic skill learning, where we have symbolic learning at the operator level, and we saw a simple example of that before. There are other kinds of symbolic learning techniques that we use from inductive logic programming and other kinds of program synthesis to learn these kinds of operators. And on the continuous side, we often use neural network techniques, which makes it neurosymbolic, but there's other kinds of choices that we might make. And what we need to learn are these parameter samplers and parameterized policies. And these are also, again, relational, which allows us to generalize over objects, owing to the fact that these are, they have arguments, and so we can give them different objects to ground these skills. So for example, what we can do with this framework is we can take something like these demonstrations shown here for this coffee making domain, where you need to heat up this pot of coffee and then pour coffee into this mug. And from about 50 to 200 demonstrations of that form, we can then learn skills that allow us to generalize to along a number of different axes. So we can generalize to new states, new and more objects, like different numbers of coffee mugs, for example, and newer and harder goals. And we've looked at a number of different domains here. We have some empirical results as well, showing that the skills that we're learning and doing bilevel planning with allow us to generalize and solve problems more efficiently and effectively than a number of baselines. Again, looking at graph neural networks and other kinds of relations. And another cool thing is that because we're doing this very structured kind of learning, it's easy for us to combine skills that are learned with ones that we know how to write down by hand. So for example, this is a sort of navigation domain where the robot needs to avoid obstacles, but also open doors. And so we've implemented a skill that uses motion planning techniques to get from like one part of a room to another part of a room while avoiding obstacles. But then we've learned an additional skill for opening doors, and now we're using bilevel planning to chain together the door opening and the obstacle avoidance to get from one room to another while avoiding obstacles and opening doors along the way. So altogether, what this gives us is this unified framework for learning all of the models that are necessary for task and motion planning, or this kind of bilevel planning. And we've done this across a series of papers where we've gradually learned more and more pieces while making sure that each of the pieces remain compatible with one another. And this is the first system of its kind where we're learning all the models that one needs to do a kind of bilevel planning or task and motion planning. So that is a little bit about my interest in learning to make TAMP possible. I have other work looking at learning to make TAMP fast, where as the robot continues to see the same kinds of problems over and over again, it gets better and faster over time. And I don't have time today to go into any of that, but we've learned a bunch of different kinds of models looking at learning heuristics and learning different ways to attend to relevant objects and a number of other kinds of techniques that allow learning to get better over time. But in the last part of the talk, I want to talk about sort of an inverse problem, which is not learning to plan, but is instead planning to learn, where the robot is going to use its ability to plan to a certain degree to collect additional data online and then learn from that data to get better at planning. So this goes back to my motivation from the beginning, where we want to have robots that can learn to specialize once they're deployed. And the kind of learning that I talked about so far is a sort of high-level learning, or you might call it like a Eureka style of learning, where we're learning these high-level concepts from a little bit of data that generalize quite a lot. But there's a different kind of learning that I think is equally important during deployment, which is more like learning through practice, where the robot's going to actively collect its own data and sort of specialize to certain low-level concepts. So if you think about something like juggling or playing piano, these are things that we don't learn by just watching videos of those things. We need to actually practice. And technically what we're talking about is often the key question of how should the robot decide what to practice in the space of things that it might decide to practice. So in reinforcement learning, this is essentially a question of exploration. It's also very related to active learning and machine learning. And I want to tell you now about a project that we just finished up at the Boston Dynamics AI Institute, where we're looking at how can we do this kind of learning through practice to learn the samplers that are useful for doing the kind of bilevel planning that I talked about before. So once again, we're going to imagine that we have these robots coming from a factory. But for the purpose of this part of the talk, let's suppose that the robots are coming to the deployment sites with a library of skills to start out with. And it also comes to the deployment sites with parameter priors, which propose reasonable parameters for the skills that are sort of good in general, but they're not specialized to the deployments. So for example, the robot might come to us with a grasping skill and might also come to us with a generic parameter selector for grasping that sometimes works, but depending on the particular setup in our particular objects might not work all the time. So depending on where the hammer is in this rack, certain grasp parameters may or may not work. And maybe we might also have a place skill, and we might have continuous parameters for placing, which is like the relative position of the robot's gripper, and certain settings of those parameters will work in some cases and not work in other cases. So what we want to do is be able to have the robot use its ability to plan to practice online and get better at planning over time. Something like this dog that's maybe planning to practice some kind of skill of using a stick to throw the stick. It's decided that's a cool thing to do. So we want to have our robot dogs, do a similar kind of planning to practice, but one that is perhaps a little bit more human motivated. So perhaps we want to have a robot that's planning to practice something like sweeping. So this spot robot's decided that what it's going to practice is the sweeping skill. And now it's using its planning capability to set up a situation where sweeping is possible. So it's taking a number of actions like moving the chair out of the way, putting that bin to the side of the table, and then finally it can practice sweeping one time. The technical question we're focused on in this project is how should the robot decide what skills are most useful to practice if we ultimately want the robot to be as good as possible at the tasks that we care about? So to answer that question, let me introduce a notion of skill competence. So this is the probability that a skill will achieve its intended abstract transition. So in the case of grasping, if we have a prior parameter selector that works half the time, then the competence of that skill would be 0.5 for that sampler that we have. If we had known competences, which we don't have in practice, but we can estimate, if we have those competences, then what we can do is we can introduce the competences into our symbolic planner and use sort of cost-based planning to end up with what's essentially a maximum likelihood abstract plan that's most likely to achieve the entire goal. So how should we decide what skills are most useful to practice? Well, one reasonable answer to that question, which was actually the answer that we started with, is why don't we just practice the thing that the robot is currently the worst at? So focus on the thing that's failing, or practice the skill that has the lowest competence. And this is intuitive, but it has two big problems that we quickly ran into. One problem is that the skill might not be improvable. So maybe we're bad at this thing, and no matter how hard we practice, it's not improving. And the other issue is that the skill that we're currently worst at may not be the one that's most important for the distribution of tasks that we want the robot to solve. So this is not looking at all of the task distribution. So that led us to this other approach, which we call estimate, extrapolate, and situate. And this is an approach where we're going to practice a skill that we estimate to be most important for the overall task distribution by actually estimating how much we would improve at the task, at the skill, and then how much we would improve the overall task distribution. So we do this in 3 steps. So first of all, we're going to estimate the competence of each skill that we have. Then we're going to extrapolate the competence. So this is where we say, I wonder if I practice this skill by this amount, how much better would I get at this skill through practice? And then finally, we situate the skill in the task distribution. And what that means is we say, okay, if we did hypothetically practice this skill and get better by this predicted amount, then how much better at the overall task distribution do we expect to get? So for the
extrapolating means you're estimating how much you can extrapolate it, or are you just thinking, what could happen if I could do this 10 times faster or 10 times better or something?
So it just means we know that say that our competence of the skill is 0.5, so we're like half the time succeeding. Extrapolation says if we practiced it and relearned.
We make it up to 7 or
exactly.
Or
how much better would that get?
It's a non-improvable skills on the previous thing.
Yep. So to do this estimation and extrapolation, we have this graphical model which combines beta distributions and Bernoulli distributions to model together the current competence and the future competences. And to do the situation part, we use that symbolic planning technique that I just mentioned, where we introduce the competences as a kind of cost and try to estimate how much better at the overall task distribution we would get. So let me sort of illustrate how this approach looks in practice. So this is going to be a sort of toy environment that kind of captures the key things that are cool about this approach. Where so this is a spot robot that's just come from the factory, say, and we're telling it to put the ball on the table. So given its initial models, what it thinks the best way to do that is to directly pick that ball up and put it onto the table. But it turns out that this table is subtly slanted. So no matter how hard the robot is going to try to put this ball on the table, it's actually not going to be possible to directly do so. So after the robot tries and fails a couple times to accomplish the task, we're going to give Spot free time, where we'll leave it alone, and it will decide on its own what skills to practice and then plan to practice them. So here it goes, starting its free time. And at first, Spot is going to decide that the best thing to practice is that place ball on table skill, because it thinks at first it's optimistic about its extrapolation, and it says, well, if I just keep practicing placing the ball on the table, then I think I should get better. And empirically, it has knowledge that its current place ball on table skill is not so good in terms of its competence. But it has this optimistic extrapolation, which is the blue bar there, which is saying, okay, if I just keep practicing, I will get better. And also it knows that it's in the task of trying to get the ball on the table, this place ball on table skill is an important part of the overall task plan. So it thinks it's important for that reason. And it's constantly maintaining these estimates of each skill competence, current competence, and extrapolating the competences in the library of skills that the robot has.
And again, the library of skills was predefined.
That's right. In this project,
A
it's
set of parameters that's all, and you just now tweak the parameters over learn.
That's right. We're just tweaking the continuous parameters. Yeah. Very good. So here the robot goes, and it's just going to continue practicing. I think one more time this place ball on table skill, and then finally through these couple of sort of trials and failures and relearning, it sees that okay, I'm bad at place ball on table, and I'm also not getting better. So now it's going to update its extrapolation to say that okay, practicing is not helping. And once it does that, it then updates its maximum likelihood plan, and it considers a different way of accomplishing the goal of getting the ball on the table. And the different way is going to involve this ring, which we conveniently left in the room there, and is going to use this ring to set up a kind of stable support on the table, which the ball can then be placed inside of. So after that, the robot then goes on to try to practice this different way of accomplishing the goal, which involves placing the ring on the table. But turns out that the table is actually smooth on the right-hand side. So when it places the ring on the right-hand side of the table, it falls off, and that doesn't work either. So it's never seen anything that's really working yet. So it just goes back to the ball. Then it's going to try the ring one more time. And then that time it did succeed, and it's going to practice placing the ring once more. And so here it has seen a case where placing the ball on the ring on the table works, and finally it's able to place that ball inside the ring, seeing the first success of getting the ball on the table. So this is all happening, in Spot's free time, and we let it sort of practice autonomously for 3 hours without any kind of intervention, except we had to change its battery once in the middle. And we can watch sort of the robot practice on its own for these 3 hours. I'll show you a very, very sped up video of that practice.
Does it know this this compositional hierarchy in advance that balls go in rings and that works, or did it have to learn that compositional architecture?
It essentially knows that through the definition of the skills that we're giving it. So the skills come with the operators, and the operators have that knowledge essentially picked up. Yeah.
It has compositionally modularity, it knows how to
Right.
just check each module and how they. Yeah.
Exactly. Yeah. So during that sped up video, what you might have seen is that the robot was spending a lot of time practicing placing the ring on the table, which is what we hope to see, because that's the thing that's actually improvable through practice and important for accomplishing the task. And so after all that practice, we can come back and we can reevaluate the robot. We can once again ask it to put the ball on the table. And we'll see that it's figured out, okay, first of all, I should use the ring instead of directly placing the ball on the table. And second of all, it did that really nice placement of the ring on the left side of the table, which results in a final success. A little bonus is that this whole system is robust to a certain kind of adversarial intervention, owing to the fact that we're sensing and replaying all the time.
They haven't trying to pick up the ball, or they.
Yeah, I mean,
Yeah.
just trying to move things around.
I'm just curious, the planner now overfits to the principle that the ball will always roll down the table, or it can replan to just put the ball first in the table?
It could replan to find that plan, but it knows that the probability of that succeeding is very low. So it wouldn't try to directly place a ball on the table anymore, because it knows that its competence for place ball on the table is very, very low. Yeah.
So you've said about this very interesting demonstration that the robot effectively knew some physics about the way balls and rings and works and gravity and all that stuff, right?
That's all known,
But-
yeah.
Yes, but you've also said at the beginning that you wanted robots that were good in general at things, like at deployment. You had this nice graphic of robots going to 4 factories, presumably doing complicated things.
Yeah.
And it seems to me that this runs into this little problem of encoding common sense in general.
Oh, yeah, absolutely.
And that's a hard problem with a lot of casualties, right? The SAIC project failed to do it after 25 years, right?
That's right.
So like, how are you thinking about that kind of stuff?
So I want my robots to come from the factory with some common sense knowledge of physics and other things that are sort of universal and common across all different kinds of deployments. And what I want them to learn during deployment are things that are weird or particular to its deployment site. So this slanted table is something that, with its sticky side on the left side, is something that probably didn't come up in the factory. So that motivates learning in the wild. Now, this particular example is actually not a great example of that, because we're talking about physics, and ideally the robot would come with intuitive physics that would allow it to recognize visually, like, oh, this is actually a slanted table, and maybe I can even see the friction on the table and reason about that. But in general, what I think is motivating is having a robot that can learn during deployment to things that are particular about that deployment, in combination with its common sense understanding of the factory.
So it sounds like your answer is it's on the factory to provide it with enough common sense, whatever that means.
Yeah.
So that sounds pretty hard. Okay, thank you.
Well, it is hard, but I think we're making quite a lot of progress. I mean, with foundation models and so on, quite a lot more to do, but yes, they're absolutely a hard problem. All right. I also want to show a bit more of a sort of not quite, it's still a bit toy, but a bit more well-motivated example where suppose that we have this playroom with these toys on the table and we want the robot to clean up the playroom. So tell the robot at first, hey Spot, put the toys in the bin. And this is again like the robot just coming from the factory without having learned yet. And so it knows, given its initial skills, it needs to move that chair out of the way to access the toys that are on the table. And it needs to use this brush to sweep those toys into the bin. It could have also picked them and placed them directly, but it decided that was a better way. But yeah, it doesn't know that the toys are too light and the sweeping is too hard. So it needs to use its free time to get better at sweeping. And so once again, we leave Spot alone for a couple of hours, and it decides what to practice and then plans to practice. And in this task, the thing that's most important to practice is clearly sweeping. So it's going to spend a lot of its time practicing that. And you know, it's nice to see like this is fully sort of reset free, where the robot is autonomously setting up situations where it can practice. So it keeps practicing and setting up situations where it can practice sweeping. So here it goes, collecting quite a lot of practice. It's about 2 or 3 hours, and with the battery change. If you watch very closely, you can see the moment where it falls on over to its side because the battery runs out, and then we come in and we change the battery. Yeah.
Part of this planning to practice could have also involved changing the location of different buckets and so on, the relative position, the distance between the table and that bucket.
Yeah.
So it seems like there are so many variations in this planning to practice. So how do you go about choosing one of them? How do you constrain it?
Yeah, so I think what you're pointing to, well, let's watch this gremlin video and let me answer that question. So one more adversarial intervention that is fun. So once again, this is after learning. And it's almost going to succeed. But here comes the gremlin. And now the gremlin, who happens to be me, is I'm going to put that basketball toy up on this ledge. And the robot sees out of his cameras that the ball is no longer in the bin, it's on this ledge. And so it also knows in its skill operators that it can't reach that high up shelf directly. So it needs to find a different way to get the thing that's on the high up shelf. And so it can use this platform dragging skill that I teased in the beginning to do that. Cool. Okay. So back to your question. So I think what your question is pointing towards is the fact that when we're deciding what skill to practice, this is just a discrete decision that we're making. We're deciding I'm just going to practice sweeping or I'm going to practice picking or something like that. What we're not doing this project, which I think is definitely important, is reasoning about the continuous states themselves. And for example, like maybe the thing that we need to practice really is sweeping objects that are on the edge of the table or on the left side of the table or something like that. So that's another sort of level of active learning and deciding what continuous states are most useful. And then also contingent on that planning to get to that state where the continuous part of it is satisfied. So that last part that I said is actually, I think, one of the hardest parts technically is because we don't have an easy way in our planner to say get to this specific continuous state. We only have this kind of discrete planning happening and then continuous optimization contingent on the discrete plan. So we would need to change our planner to get to a state where a specific continuous state. We do have a project that does that, which I won't go into too much detail, but we changed our planner to basically consider like many different kinds of continuous plans that are consistent with the abstract plan, and we picked the one that is best from the perspective of active learning. So I can go into more detail about that later. But anyway, your question is very good. Yeah. Yeah.
So here at Hopkins, people do a lot of medical robotics.
Yeah.
And one worries a little bit about practicing being dangerous.
Right.
So have you thought about practice in settings like that?
Yeah, absolutely. So I certainly wouldn't want to have like a robot playing to practice in an operating room or anything like that. I think that one thing that would be powerful that would help with safety and help with a number of other things is if we have the robot generate its own simulation of the real world and then plan to practice inside of that simulation. So naively, we could just have, a way to go into a physics simulator and then the robot plans and practices inside of that physics simulator. That would also simplify our lives a lot because we wouldn't necessarily need to plan to a state where practicing is possible. We could just, set the simulator to be in a state where we can practice and then much more efficiently practice inside of that simulation. So that I think would be useful in settings where safety is important. Another thing that I think is very interesting in that direction is what if we have the robot be able to generate its own, decide what level of fidelity to model things at in the simulator. So decide what objects are being modeled there, what physical properties are being modeled. So I'd like to develop a robot that can like be, in a real world and then go to sleep and then decide what level of fidelity am I modeling the real world so that I can plan to practice in my head and then wake up and be better. So that's the direction I'm very excited about, but definitely an open problem. I think there's a couple of hands online. I don't know if, there's one here too.
Thanks for the nice talk. You've been focusing on things that you've done. Sort of backwards in time.
Yeah.
Usually the sort of talk that the speaker spends about at least a third of their time talking about what they want to do.
I'm not done with my. No, I was just about to get to that. Yeah.
But over the next 5, 10, 50 years.
Right.
So could you speak a little bit about what you see in the future?
Yes. I think, okay, some empirical results, but then I think I'm about to answer that question. Yes. So, so the hope is to, over 50 years or so, develop really this general virtuous cycle where learning improves planning and planning improves learning. And I think what's most important is that we continue to make progress on these two axes where we have robots that can operate over longer time horizons and can solve much more general kinds of tasks. And there's a lot, of course, to do here. One thing that I think is a sort of short-term, very interesting direction is looking at what ways can we take advantage of foundation models in order to learn abstractions and that are going to be most useful for this kind of planning and learning with abstractions. And so one thing that you might do is use foundation models to propose maybe the pool of candidate predicates that you're considering instead of using this domain-specific or domain-independent grammar that we have. Use something like a foundation model to propose predicate candidates and then search in that pool of candidates coming from the foundation models. But generally, this theme of using foundation models kind of as a prior on top of which we're doing additional learning, I think there's a lot to do. Another thing that I'm very excited about is sort of working towards a robot that can sort of program itself. So like you leave the robot alone and it develops like a library of code analogous to how we have our own code libraries, which have all these utility functions and abstract base classes that call each other. And as we're constantly in the process of adding more code, we're also refactoring code and we're unit testing it and so on. And I really want a robot to be able to do all those things as well. And I think there's tools that we can take advantage of in program synthesis to do some of these things that we haven't fully leveraged in the robot planning community. So there's a lot to do there. To really go over longer time horizons, I think it's going to be important that we're not just planning over 2 levels of a hierarchy, but really multiple levels of a hierarchy. So the robot can plan over days or weeks and then break that down into what should I actually do in this moment to accomplish a super long-term goal. And ultimately, the 50-year goal is really how can we develop what will be a full stack cognitive architecture for generalizable robotics? And I think that learning and planning will be central components of that effort. And so with that, I'll wrap up and just say thanks to my collaborators and advisors. This is all very collaborative work across many different folks at MIT. And I'll say thanks for listening and look forward to more questions. Thanks a lot.
There's some questions online, but I would take in person.
Okay.
Jason?
We don't want to take online for a second.
No, yeah, in a second, but maybe person first.
Okay, yeah, so can you say something about discovery of abstractions? I think you alluded to that along the way. It's very nice when a robot comes out of the factory and it already knows about some things, but there might be additional task-specific abstractions that it has to discover from the raw data.
Yeah, absolutely. So the predicate learning work that I was describing is, I think, an example of that, where it's discovering predicates on its own. There's quite a lot of structure that we're starting with there because we're starting with this grammar, but we're still sort of discovering or inventing predicates in that way. And then we invent skills that are using those predicates. So that's all sort of speaking to the skill or abstraction discovery part of my work. So that was like an extreme case where we don't start with any abstractions and we try to learn all of them. This last part of the talk was the opposite, where we start with quite a few abstractions and we're just sort of fine-tuning them by learning samplers. I think what would be nice is somewhere in between where we have a robot that comes from the factory with certain skills and then learns additional skills that maybe fill in the gaps in its knowledge so that it can complete demonstrations that are shown to it or like do one more thing that it needs to do to accomplish a goal. So I think the right answer is somewhere in between like those two extremes.
Even in the first case you described, though, it's the predicates that it's learning are still based on some predicates. They're not based on raw sensory data, right?
That's right, yeah.
So the connection that I'm trying to make here is in NLP, we used to write down a lot of knowledge by hand. And it turns out, as I was saying in our meeting earlier, that it's just discovered very nicely from the raw text signal.
Yeah.
And so I wonder if there might be something similar here.
Right.
Maybe you still want to use discrete representations to regularize.
Yeah.
Like, maybe they really are either useful for planning or they really exist in the real world or something.
Right, yeah, I would love to, so the object-centered representation that I described is all hand-coded, I'd love to learn that as well. And I'd really love to learn it in a way that is like downstream useful for fast and effective planning. So if we could have an objective that, for example, we could differentiate through, which this objective that I described is not differentiable, then maybe we could learn everything, including the object-centric state itself, or even being able to detect objects in the first place. That would be, yeah.
So just a little bit more about simulators, because I think if you want to apply this ultimately to every possible house, it seems like you almost need a gigantic simulator or something that could be configured to do everything. So it seems one component of all your planning is the need to construct sort of an environment. If I understand that a lot of your work is you construct this particular environment that you've been showing, that could do certain things, demonstrate stuff, but to really scale it up, it seems you need, well, a gigantic virtual world or something.
Potentially a gigantic virtual world, or we need to have the robot be able to generate its own simulator.
If it can generate its own virtual world.
Exactly right. So it doesn't necessarily need to be gigantic, but it needs to be tailored to the robot's environment. So the robot should, come into your home and be able to invert what it's seeing into some simulator that captures what's most important for learning and planning in its simulator. So,
But even the most benign sort of physical interactions like friction are still not that well captured in these engines. And so if you're doing something like fine scale manipulation, you really have to engage sort of actively in the environment. And I'm just sort of wondering, like, it's one thing if you're given a pile of text and you have to learn a set of patterns, but if you're actually in the driver's seat and have to figure out what data to collect in order to furnish a model that's sufficiently accurate, I'm just wondering if you have any thoughts on how you would engage, sort of think about it in that way. It's not like you can just be given a bunch of successful completions of a task because this is the robot sort of supposedly going out there and developing those competencies. How would you sort of structure the problem so that you could do the exploration learning of the predicates as you're following them, given the fact that simulations are doomed to succeed and they're not going to necessarily reflect the most important subtle nuances of the interaction that are going to happen when you actually deploy the machine in the real world?
Yeah, absolutely. So I think that what would be a step towards addressing that very hard problem is a combination of simulators that we know are not perfect and data that we collect online, maybe to correct the imperfections in the simulator. So the last part of the talk that was a case where we don't have a simulator and we're just collecting data online and learning from that. But in other cases, we've had a simulator and used that simulator. So somewhere in between would be something like a residual approach where we start with a simulator that we know is imperfect, but it has some common sense understanding of friction and so on. And then we learn to correct for imperfections and learn maybe a specialized residual model from data that the robot collects online. So doing that in a way that's more data efficient or sample efficient than starting from scratch, but is more accurate in the tail than just the simulator on its own. But certainly a very hard problem.
By the way, I apologize for coming in late. I had to watch from my office until I came in, but I was on.
No problem.
So there are a couple of online questions. I'll just read them. So one is, to what extent have you thought about avoiding creative solutions that robot finds that are highly undesirable, like such as you want to put the objects away, but you just smash them, so you don't need to put them away.
Yeah, that's a great question. Yeah, so one thing that I like about this whole planning with constraints framework is that potentially we could add constraints into it and then continue to solve these constrained optimization problems in a similar way. And so those constraints could be safety constraints that, for example, encode things like don't smash objects or so on. But doing that in practice is very difficult because representing those constraints is quite hard. And so there's certainly a lot of technical challenges there. But I think this framework, at least in principle, can be extended to incorporate things like safety constraints.
Right. And there's another question about failure. So you focus on test failures, which is very powerful, but would you approach help robot that has subsystem failures?
Subsystem failures.
Yeah, so actually, Jane, could you clarify what you mean by subsystem failures? I think maybe unmute yourself. Jim, okay, I think probably has that.
Okay.
So I'll go on to.
Yeah.
So, how do you think of how to handle the possible errors in the learning that may propagate into downstream test errors? I guess also relevant to the James. So if you have errors in your learning, how do you I guess mitigate those errors?
Right, yeah, how do we deal with errors in our learning? Yeah, that's a great question. So, I mean, one answer is continuing to learn from the errors that we recognize as errors when we're running these things online. So I like the direction of sort of continual learning, lifelong learning, so we're just getting better and better. Another answer goes back to having a simulator where we can sort of test out things in simulation before potentially doing risky things in the real world, and then we can recognize errors before we go about actually executing them. So those are a couple of quick answers to that question, but yeah, we're going to have errors. And another thing I want to say here is all of these systems need to be risk aware and uncertainty aware. So we should also be modeling our uncertainty about whether we're going to have errors during execution, and then planning with that uncertainty. So they're kind of like competence aware planning that I described at the end is a very simple form of planning where we kind of know that there are errors in our current skills, but more generally, we should be able to plan and reason with some estimated uncertainty of how the skills are going to work and our our perceptual uncertainty and all the rest. So yeah, incorporating uncertainty.
So any questions? Yeah.
So I'm a freshman right now and I'm like really interested in this stuff.
Great, thank you.
I'm a electrical engineering, computer science double major. And I was wondering just like, what would you give advice for like starting off in this, I guess, industry?
Oh, wow. That's a great question.
This is the teaching part of the interview.
Yeah. Well, if you're excited about these directions, then find a project that seems really cool and just start working on it. I think like there's no substitute for just hands-on experience, just hacking on things that are most exciting to you. So if you're specifically interested in this stuff, I'd be happy to talk offline about. You can use our code. We have a couple of onboarding projects that we give to people that are starting out. There's a bunch of different threads to explore that I think freshmen can explore, and I've worked with freshmen before. So if you're super interested in this, happy to chat. If you're just generally interested, I can also point you to a bunch of references, but just hack.
All right, thank you.
Maybe one last question. All right, so I guess that's it. So let's thank Tom again.
Thank you.
This is earlier in your career to be discovering the secret tools.
Yeah. Yeah, I stayed here during break, so I was like, might as well just attend as many events as I can.
I think when I was another grad, I was a senior before I figured out that there were other options.
Yeah.
Okay.
Yeah.
I think tomorrow we're gonna start. I don't have the dates on. Sir, the gate is now open.
Excuse me, so what was the
Yeah, so
Yeah.
so you should email me, but the code pages are they're gonna next.
From the load, I mean, not exactly about them.
Actually,
Yeah. What is?
like the abstract line part. And there's a bunch of different things that you might try to learn.
So
The game or
the
like
process.
policy that tells you how to solve the problem.
All the time.
That you can do.
The process is, we want to,
Okay, so this is basically like an interface to that, which has the kinds of abstractions that I was talking about. So, there's a bunch of different requirements, or if you want to do more like robotics directly stuff. The other repository we have is called Ready Papers. So this is like implements all the papers that I was referring to here. And it's a little bit it's difficult to get started, so if you actively want to do it, email me and I'll tell you how, like the onboarding
They
stuff
said,
that I'm talking about, because it's not online, but I can send it to you.
I'm not sure yet if it's an
But yeah,
outright
right,
no, or if it's
Yeah,
a
is your
like,
email listed on like the
no, and I
line?
can work on it, or
Yeah,
if
if you
it's
Google my
a,
name, then-
like,
Okay.
no.
There's a
like,
hypnotist
like,
named Tom Silver,
So,
not hypnotist, I'm.
So,
Right,
even if
right.
CS isn't,
Thank you.
even if CS is enthusiastic and has certain views about like where people should be,
Yeah.
that doesn't mean that we get to make that business go on. So we have to make that case. Randall, I think, collected information so that he could now go make that case. But that case is committed.
Oh, I didn't realise they were. I mean, I thought.
There
this
is
was
not
sort
a
of
rubber
just the thing.
stamp.
I didn't really realise that.
I
PSS
got
was involved in-
I got pushed
in
back
that
from someone else today.
Yeah.
Really detailed,
Hey, Tom.
like reading your papers.
Hi, Tom.
And
Oh, hi.
letters,
Are you coming to lunch?
and then.
Yeah,
like,
great, awesome. Yeah, I think the others are just coming back.
So
Okay,
so it's
gotcha.
not, it's definitely not.
Actually,
That's
And the provost office.
And the provost office to look at these.
They really are.
Well, in one sense, this is good, in the sense
It's good, it makes me work hard.
right, because. I mean, if
That's the reality.
when there's a real director and a real, full thing maybe, but
Yeah.
Anyway.
Hey, Tom,
that's cool.
I'm Mark Redzi.
hi, nice to meet you.
Sorry, I'm not in your schedule.
Oh, that's
but
all right.
You're quite busy.
Yeah.
So I wanted to come over and say hi and
Thank you.
introduce myself. This
Yeah.
was fantastic.
Thank you so much.
I think my favorite part is not you, but my favorite part is there's a moment when the robot's about to do something and it moves all 4 feet, but it doesn't move positions.
Yeah.
And it's kind of like the cartoon excitement.
Yeah.
I'm like, oh,
Can't wait.
yeah. I know I'm anthropomorphizing, but like, I just thought that like, it's like, oh, good, I get to practice this skill. So it was great.
Yeah.
I really enjoyed this very
Like a
much.
dog.
Thank you, and enjoy the rest of your visit.
Thank you so much.
And you know where to go next, do you?
The students are coming back.
Okay, good. Pick you up, right, because that should be about now, I
Yeah.
think.
Yeah.
Yeah. Sounds good.
Yeah.
Okay, well, look forward to talking. to you
Yeah, me
later.
too. Thanks.
Yeah, I think it went very well.
Good presentation. Thank you. A little bit more sharply worded questions than I'm used to, but hopefully it doesn't seem defensive or anything.
No, that's good.
Okay.